Good afternoon, Dr. Satwinder ji.
From my side, sir.
Namaskar, Satwinder ji, Dr. Satwinder ji.
Can you listen to me?
Yes,
Am I
yes,
audible?
yes,
Okay.
yes, yes,
Yeah.
yes, yes.
नमस्कार सर, नमस्कार.
नमस्ते, नमस्ते. आप कैसे हैं?
बढ़िया हूँ सर.
हाँ. We will start within 5 minutes, sir.
Sure, sir.
So, if you would like to share your screen, please check it.
Okay, I'll do that. Can you see my screen?
No, sir. No, sir. Earlier, the screen was visible. Yes, now it is visible, sir.
It's in the slideshow mode or the...
No, it's not in the slideshow mode.
Okay.
Now it is visible, sir.
In slideshow mode.
Slideshow mode. Yes, sir.
Okay. Thank you.
So, sir, we will wait for another 2-3 minutes. Then.
Sure, sir.
Good afternoon to all of you. It's a great pleasure and honor for me to introduce our session 9 speaker, Dr. Satvinder ji. He will deliver a talk on surgical robotics. Before inviting Dr. Satvinder for his talk, I would present a brief profile of Dr. Satvinder. Dr. Satvinder did his BE in mechanical engineering from IKG Punjab Technical University, Jalandhar. Then he did his MTech in design from Punjab Engineering College, University of Technology, Chandigarh. Then he did his PhD in robotics from IIT Ropar. And presently he is working as project manager, NSERC PDF fellowship in a hospital for sick kids under University of Toronto, Canada. So he did his after doing his PhD, he was the junior and senior research fellow at IIT Ropar. After that, he was the research scientist at Biomedical Engineering Limited, Hong Kong, and he has published nearly 15 papers in the international journals and conferences. And he is having an exposure, a good exposure on surgical robots. It is a very emerging area of research. So I would request Dr. Satvinder to unfold his presentation. Dr. Satvinder, please.
Thank you. Thank you very much for your kind words. He already gave my brief introduction. So after that, after my PhD, I went to Chinese University of Hong Kong, and in Chinese University of Hong Kong, there was a startup company, Biomedical Engineering Limited. Till my Hong Kong stint, I didn't know anything about medical, and there was only one page written in my thesis about the medical robots. So accidentally, I got the exposure in the medical robots in Chinese University of Hong Kong. My first project was MRI breast biopsy mechanism, and I went to that incubation center and I entered as an assistant research scientist because that company was funding my postdoc. From that company, and then next year I went to that company like as a full-time employee, and from that company I went to Italy in Dr. Bruno Siciliano. I think he's a very big name in robotics. I went to his lab for 1 year to do some research, and I submitted 2 Italian and 2 European patents over there in medical robots. And that was also related to the surgical robot. From this, now I'll show you the contents. I'll try to be a little bit less from the heavy from the medical side, so that you all can understand that what I'm trying to talk about. So first I'll go for the introduction about the surgical procedures from the very basic, that open surgery to the nodes, which is currently going on. Means what is the role of robots in the surgery. And then I'll also try to explain that what are the challenges of robots to be in the operating room. And then it's notes, and then I'll try to explain something which I worked on MRI compatible robots. Then I also worked in colonoscopy also. It was a soft colonoscope. And then in my current role, there is one of my colleague. He's a cardiologist, and he's using 3D printer to guide their medical professional people. Basically, with the 3D printers, they can print the hearts and the brain, so that the medical students can learn something. They can try to do some surgery on those 3D printed hearts. And now that system is going a little bit forward, and the doctors are doing practice on that surgery, on that heart before the surgery. So I'll try to explain all those things and you can ask questions, whatever you didn't understand, you can ask me straight away, and or maybe you can note down and then ask me later on, and then note down the slide number that where I spoke that thing. And but the only thing is I will try to be a little bit more less heavy with the medical terminology. So I'll start with the surgical procedures. So currently we have these type of surgeries: open surgery, manual laparoscopic surgery, robot-assisted surgery, robot-assisted single-port laparoscopic surgery, nodes. Nodes is currently on which I am working on. Open surgery, as the name suggests, open surgery means they open. And one more thing, I'm talking about the abdominal surgery only. I'm not talking about any other surgery because my field, what I'm doing right now is the notes on the abdominal field, abdominal area, gallbladder, liver. So these kind of organs I need to remove. In the open surgery, they just open up the abdomen, the top of the abdominal wall, and then they can access the side. They can you do whatever they want because they have a free movement of the hands. And in manual laparoscopic surgery, this is the picture. Manual laparoscopic surgery, they insert. There are 2 or 3 incisions. That with that incisions, those small incisions, they will insert the laparoscope and they can access the target site. But the problem is if there are 4 different quadrants. So if they entered into one quadrant, in that one quadrant, they can only access that quadrant only. So if there is some blood loss in some other organs in the other quadrant, they need to do another incision. So like these are 3 or 4 incisions. One incision is for sure for the camera. 2 incision is for the laparoscopic tools, and 1 incision is actually for if they want to remove something, like if they need to cut the gallbladder or cut the liver, they need to remove that sample. So those incisions are there, and if there might be another incision, because if they cannot reach that access, they can not reach that site and cannot access it properly. So they need to do another incision and insert another tool. So, but for sure that in comparison to open surgery, the blood loss will be very less in this particular case, and the post-operative pain will be less, and the stay will be little bit less as compared to the hospital stay will be little bit less compared to the open surgery. But open surgery, as I told you, that they have a full advantage of the target site. So doctors can easily access all the organs once the abdominal wall is like the tier of the abdominal wall from the top. So it's the natural ergonomics. Can you see my what I'm doing right now? Can you see my video?
No, video is not coming, sir. This screen is coming.
Oh, okay.
Robot-assisted laparoscopic surgery.
No, not video. Like, can they see me? I have like my video is on.
Okay. That slide is coming. Slides are coming, sir.
No, I'm talking about that. ये मुझे देख सकते हैं कि
मैं
क्या कर रहा हूँ?
No, sir.
Okay. So what I was trying to say that it's a natural ergonomics, like the way you are working on laptop.
Now your video is on, sir. Now your video is on.
Okay, so they can see me. So you can see me what I'm doing?
Yes, sir.
Okay, so what I'm trying to say that what is the natural ergonomics means that if the patient is here and I'm doing this is the natural ergonomics for me. So it's very easy for me to operate on the patient. But when I'm inside the laparoscopic tool, I am I'm bound with the boundaries of that tool, because tool is inserted inside a cannula. We call it cannula. Through the cannula walls, I need to just use my wrists only. Here I can use my whole arms. So that is the only wrist thing and the degree of freedom which my tool has. So that's the thing. So after this, so this is not a robotic, this is manual laparoscopic tool. And manual laparoscopic tool is that the tool will be at least 25 to 30 mm long. And the torque I'm using here, some clipper I'm using here, and the torque they need is at like 25 or 30 mm away from that clipper. So that force is also not that adequate. So after this, we went, the research went to the robots. The robot. Sorry, so this slide should be before. So then they went to the multi-port robot system. This is currently going on right now. This is the system which we are using in all the hospitals, like 95% hospitals they use this system. Multi-port is same like the manual robot. One tool will be the camera, and tool will be the tentacles which they want to use. Like one will be the clipper, the another will be the scissors, something whatever they want. And there are some more tentacles like 5 or 6 arms, so they can change the arms. Each arm has a different tool, and depending upon the condition, they can change the arm. And this system is also like I wrote it Da Vinci Si. This was the first. This is the latest system, Da Vinci Xi. Raven 2, Raven 4 were the systems which I used in my thesis, and they are now obsolete. Nobody used that one. But the difference between Da Vinci Si, Da Vinci Xi, Da Vinci currently the system we call it DVRK, which Da Vinci gave to all the universities. So the difference between that is there might be a uh, fixed incisions, fixed holes, and in the current system they can interchange the holes. So previously there was like there will be on the left side there will be one tentacle, and for sure that will stay over there. And in the middle there should be camera, and on the right side there will be the another scissor. So that scissor cannot be on the left side, but with the current system they can interchange that system, and they can interchange that sites how they want to access. And with this system they can have a little bit less incisions instead of having more incisions using the previous system. So if they want to access gallbladder, or if they want to access kidney, they theoretically there should be only 3 holes. So what I'm saying, theoretically 3 holes, one camera, 2 tentacles, but there are at least 4 holes, because if they want to remove the sample they have to have another hole which should be bigger than 5 mm, 5 to 10 mm. So with that incision they will take away that sample which they want to remove from the body. And I'm saying this thing that kidney, gallbladder, I'm doing like this. So I'll give you a little bit history about that. The history is these systems were designed. They were like the project was started when there was a Gulf War between US and Iraq in 1991. And the problem it was funded by DARPA, that the US Defense Organization. It was funded by them, and the concept behind it was that robot will work. I'm talking about 1991. The robot will be installed in Iraq or in Gulf, wherever their US soldiers are, and cardiologist will stay in US, and they can operate with the robot there on. And I'm talking about cardiologist. So and the quote unquote I'm saying because I met that person who was in the team and who was the one of the first person who designed this robot, that all the researchers, they target the heart, but they shot at abdomen or groin region. So the design was supposed to be work on heart. Means it's for cardiology or cardiac surgery, but 98% robots are working on groin region, means kidney, gall, means this lower part, lower abdomen. And total 98% is working on groin and abdomen region, and only 1% is working on heart, and that's also not for cardiology. It's for some other surgery. Why? Because they didn't take the constraint of pumping heart. The heart is moving part. They didn't take that constraint into consideration while designing the robot. That heart is pumping. It's not like a organ which is not moving. So that's why, because of that pumping ability of heart, they cannot use the robot. So that's why that person who designed the robot said that we shot like aim at somewhere else and we shot something else. So apart from that, this was the brief history why it was started and for what type of surgery they want to do. Now the research is going towards the single port system. So at that time I was saying that the multi-port system where we have 3 different ports, the 3 different incisions, like 3 holes in the abdomen. But now we want a single port. A bigger cannula will enter inside the abdomen, and from that bigger cannula, and I'm talking about bigger cannula means at least 25 mm size, the 25 mm hole, 25 mm diameter of hole will be inside the abdomen, top of the abdominal wall, and then they can access the site. From that 25 mm, they can introduce 3 tentacles at least at one time, and then they can work with that. And the problem there is like there are 2 different mechanisms, like tendon driven mechanism will be little bit better in terms of the size. And then there is an in vivo actuation, that motors will be inside the moving parts of the robot. So there are different drawbacks like collisions of instrument due to the like coaxial arrangements. We call it chopstick effect. And then the profile is very bulky inside the like operation theater. So you cannot really move, you cannot reposition. Once you are inserted for that particular site, and if there is something else, you cannot access the abdominal cavity once you are inserted. So in the in vivo system, the torque is very less because motors are inside the links, and the incision size is also bigger as compared to the tendon driven. So I was basically working on in vivo actuation, and I have a personal experience in industry while doing the cadavers. Cadaver means dead bodies. I personally used this system on the dead bodies and on pigs. So there was some problem. So these are all in vivo. These are all single port systems. So in single port system, like, can you see me again? You have to focus on me now. Can you see me? Hello?
No, now you are visible, sir.
Okay, so what I'm saying that when we were using the open port system, this torso gives me a natural ergonomics. But when I am inserting, I'm talking about robots. When I am inserting, all the tentacles are like this from the single cannula, and then they need to go out. So when they are going out, we are losing 1 degree of freedom just for the ergonomics, just for the positioning. We cannot work like this. So doctor need to do like, there should be some distance between this, what our torso, this torso is giving a natural ergonomics. The same natural ergonomics is required inside the patient's body. So what we are doing, we are inserting from a single cannula, and then 1 degree of freedom is required only to get that torso inside the body. So we are losing 1 degree of freedom inside the abdominal cavity while working with a single port system. So the main advantage is that the trauma will be minimized, and the complication will be less, and the scars will be less. And I personally think that scars is just like a mental part, and the post-operative pain and the wounds will be less theoretically. So it's not published yet that how much effect and how much percentage that wound infection will be less than the multi-port system. So out from this, so this we already covered, and this is a single port laparoscopic surgery, and you can see that. So this was, I'll give you a brief background. The Titan Medical, I was thinking that this might be a big thing. And Da Vinci is Intuitive Surgical's robot. Intuitive Surgical has a monopoly in this whole world, like 99% of robots are from Da Vinci. And 2001, they started 2003 they started different Da Vinci from Zenith robot, and currently they have there is a patent war between different new companies, because the previous patents are going to be expired soon for Da Vinci system. And Titan Medical was about to launch their system, and it has been overtaken by Da Vinci. So Da Vinci, and I will show you the colonoscopes, Olympus colonoscope, they have a monopoly. If somebody is coming up with a different design or different mechanism, they just take over with their money. So this Titan Medical 2 years back, it was good. It was like going and about to launch their system, and now it's shut down because Da Vinci bought this company.
Yes, sir. You are sharing your screen.
Sir, you were asking something?
Yes, you are sharing your screen right now.
It's not video is not working.
No, sharing is in progress. It is showing like this. Sharing in progress.
I'm sharing my screen, so it's not. You cannot see the video.
No, sir. You just share your screen. Some video issues are there.
Okay, so you cannot see the video. Okay, I'll try to do it in different way. Can you see now?
Yes, sir. Yes, sir.
Yes, sir.
And it's audible also, the video.
No, voice is not coming, sir.
Now?
No, sir.
Okay, I'll give you the brief here. So what they are saying, that there is a cautery system, and in this cautery system, one is a grasper and another is a cautery hook. So cautery hook has some current inside it, and then we call it a monopolar also sometimes. And grasper will hold the skin, and the cautery will just cut the tissues using that current or heat. So that's what they are trying to say, and they mentioned 7 degrees of freedom. So that is a very important part. 7 degrees, it's not 7 degrees, 6 degrees. The 7th degree they are talking about is the grasper's movement, that how it will hold it. And because we are using the system, master console, and using our wrists, we cannot control 7 degrees of freedom with our hands basically. So we can only take 6 degrees of freedom. We can take control of 6 degrees of freedom with our hands, with our wrists. So 7 degrees of freedom, even my system, when we presented our system, that we had a 7 degrees of freedom. Yes, we had a 7 degrees of freedom, but the 7th degree of freedom which we introduced was only to hold the position inside the abdominal cavity, so that they can have a torso, proper torso. 7th degree of freedom was actually locked while doing the procedure. So we were just controlling 6 degrees of freedom. 7th degree of freedom was there just for the torso. So that's the important part here. So now you can say that, see here, this part, what I'm showing, this is the cannula. This is theoretically the abdominal wall when they introduce the abdominal wall, but they can only concentrate on this part. But if something else is happening on the literal right side or the left side, these tentacles cannot reach, and even the camera cannot focus on that part, because they need to turn on that side, and the tentacles angle will be like that one tentacle will be stretched, it will be fully stretched, and the other tentacle will work in some awkward position. So in that, because it will be on their extreme positions, they cannot really work. So that part is the problem. So they need to rotate this part. So if they are rotating this part, or they are just turning this part to their target side, it means they are stretching the outside wall of the abdomen. So that's what I was saying, that if they are inserted inside for that particular target site, they will just work on that target side. They cannot work on different target sites. So if they are inserted towards this part, here is gallbladder and liver, so they can work only on this part. They cannot work on this side, or if something happen in the kidney, they cannot work, which the doctors can access while doing the open surgery. So this is just now the suturing part, just to show that how it moves. The movement is very good, something like that. So the thing is, after this we are going to notes. What is notes? Notes is a natural orifice entry. So first I'll show that this doctor is sitting and the patient is lying over there. I will come to this part later, that there is something wrong here, and the doctor is sitting over there, and he is using those master console to control all these arms with his wrist. So that's why I was saying that they cannot control 7 degrees of freedom. These are the like mechanism. These are the challenge tendon driven robotics. We already did that. They are bulky. You can see the bulkiness in the footprint of the robot is too big. So one operation room is just taken over by this robot, and when the real operation is going to happen, there will be different people standing over there. It's not that clean. The room will not be that clean. I will show you later on that what will be there. And the bulkiness we need to reduce. If the footprint inside the robot will be too bulky, it means we cannot change the direction inside the abdominal cavity. So the smaller robot only can change the target site while inserted inside the body. So we call it, now I'm talking about the spaghetti syndrome. The doctors are working, there are too many wires there. So this is the actual condition when the robot is when the real operation is going on. So we call it spaghetti syndrome. In this spaghetti syndrome, if the doctors are there and there are so many people and so many wires are there, they might like tangle, their instruments might tangle into that system. And the new people, because working on a real surgery, at least 1,000 hours are required for any surgeon, a junior level surgeon, to work inside the operation room, and at least 5,000 hours of experience with the real conditions is required for a doctor to become independently doing that surgery. So those many hours are required just to avoid this spaghetti syndrome. The spaghetti syndrome is just like that, the noodles or spaghetti, because the wires will be like that. So the doctor will see all those wires and tangled into the instrument, into the organs. So this is the concept. So on the left side, the concept is so clean room, the robot is there, and then nothing will be there. But on the right side is the real thing, that so many people are working over there, and and doctor, if the doctor is sitting away on the master console, he will lose that cognitiveness, he will lose that connectedness to the real operation. So those are the challenges. So like this is the challenge. This is the doctor is sitting over here. Patient is lying like 5 or 6 feet away from him. So he doesn't really know that what is the situation. And the second thing is we don't have a haptic feedback. So this is a takeaway for all the students who are working in this field, that there's till date there is no haptic feedback in any of the world's greatest surgical robotic system. Everyone is working on haptics feedback. So haptic feedback is when, like when you are touching something, some skin, your fingers know that how hard I should touch, or how much hard you need to touch to hold this, and what is the texture of the skin. But when you are holding with a metal piece and lying like sitting like 6-7 feet away, using this system, you don't feel that thing. You don't know how much force you have already put on that soft tissue. You might rupture the tissue only to hold it like little bit more harder. This might give another extra complication in that procedure. So we are dependent on the patient side robotic assistant. So there is a robotic assistant on the patient side. He or she, when we were doing the cadaver trials on the dead bodies, so one person was noting down. I'm talking about my experience. One person was noting down what doctor is saying, what assistant is saying, and what is required at what time, just to note down that how many times doctor need assistant's help, and how disconnected doctor was with the patient. So the communication should be very strong, but there is a big chance that we are like there is a breakdown in the communication, because doctor is looking towards the screen, and he get that artificial 3D effect by using that screen. There is an artificialness in that, the depth of the operating site. So he really doesn't know that how far he is inside the abdomen, how far away from the tissue, and sometimes he just grabs something else, but he needs to grab something else. So there are some other tissues. So these are the problems with the robotic system, and the takeaway is haptic feedback is not there, and it's really required. So after this, I was saying that nodes. So what is nodes? Nodes is actually a natural orifice transluminal endoscopic surgery. Nodes can be transoral, transnasal, so that is also nodes. We are using all the natural orifice to enter inside the abdominal cavity, to enter inside the human body. So transnasal and transoral are there, and they should be really small, and and I'm currently not working on that system. So my focus is on transvaginal and transrectal, because in women after 45 or 40, like 50, there are more chances of doing the surgery to remove the ovary, to remove the fallopian tubes, all type of other reproductive systems, because there is a big chance to develop a cancer in those areas. So that's why this system is currently working on, and most of the surgeries are going on using the robots on these areas. So that's why we started focused on the nodes, natural orifice. So we are entering through vagina inside the abdominal cavity. So this is the gallbladder is like 32 centimeter away from posterior fornix of vagina. So vagina fornix is inside the body, 13 centimeter inside the outside part of the vagina. From there, the distance is 32 centimeter. The 32 centimeter is the average distance. And this average distance will change. Maybe there is different. No. This average distance we have taken from the one Japanese study. So currently I'm doing study here on different ethnicities. I might sound racist, but with the different ethnicity, the distance of gallbladder from vagina fornix will change. So 19 centimeter is the smallest distance between vagina fornix, and 37 centimeter was the biggest. So this way we need to change the insertion of cannula. This cannula is the round, big round tube from which those tentacles are coming out. So we need to insert a little bit more or a little bit less just to avoid just to reach the target site. So these numbers that I'm giving to you from the Japanese study, and we know that in Japan, the Japanese women are not that tall or that big like the white Caucasian or the black. So for different ethnicity, there should be a different study, and we don't have the data for all the ethnicities. So this is actually this study was taken by a manual laparoscopist who want to design a new laparoscopic instrument, and just to see that whether he can reach the target site or not. So accidentally we got this, and currently I am doing this data analysis to get the universal solution for to reach the gallbladder. So this is the design part that what I want to do. So there is a sacral promontory. We call it a backbone or something like that. That backbone is protruded in some people and less protruded in the other people, and because of that, that is one of the biggest obstacle while inserting the robot. So like in scenario 2, if we are inserting a little bit less or a little bit more, when the robot tentacles will be inserting inside the abdomen, they might collide with the top of the abdominal wall depending upon the angle of insertion of cannula. So if sacral promontory, that the backbone is little bit more protruded towards inside of your this abdomen, so your cannula will be little bit tilted towards the top of the abdomen, and you might be colliding with the top of the abdomen, or you will go away from the target site. So these are some of the conditions. And then we need to also focus on that where should be the base position of the cannula, and how far is the gallbladder. We need to design the length of the robotic arm, which can go for the universal solutions. So there might be there is a case that for some of the patients we cannot use this cannula because of the acute angle of the sacral promontory. So we need to just see that, okay, for this patient we cannot do, for this patient we can do. The second thing is for some of the patients, because of the height, we cannot insert cannula. We need to exclude those patients already, because if I'm talking about the from the perspective of selling the robot to the hospitals, because doctors or robots, the hospitals will not buy a robot with like 5 or 6 different type of robotic arms. That okay, for this patient we need to insert this robotic arm, and for this patient we need to, because one robot is approximately is 2.3 million US dollars, one robot. So they need to like really focus on one universal solution. So these are some of the challenges from the surgical robotic side. So I will now focus on what I did in breast biopsy mechanism. So this is the second part of my this talk. That currently what is going on, I'll just give you a brief introduction about the breast biopsy mechanism. If there is some lesion or cancerous tissue in the breast, what they are doing, that the lady will go inside the MRI room, and then they will locate the lesion, and then the lady will come out, and then they in the different room they will insert the needle, they take out the tissue, the sample of the tissue, so that they can test it's really cancerous or not. The problem is the breast is a soft tissue, and whatever the location they located inside the MRI room, they might not get the same location. So what is currently happening? So this process, what I explained, that in MRI room, locate the tissue, they come out, they see that they really took the tissue from there or not, then they'll do it again. At least 5 to 10 times they need to insert the needle inside the breast to take the tissue out. So take the tissue out is actually plucking the tissue from the breast inside the breast and taking out. So it's really painful. So what we were trying to do is we were doing the MRI compatible robot, and in this, that lady will go inside, they will lock the breast at a one position, it like fix, tighten up, and then they will do the measurements where the cancerous tissue is, and then they'll insert the needle with this MRI compatible robot and take the tissue out for the sampling. So it should be only one incision for, per sample. So what we did, I think, yeah. So this was my first project. It's all 3D printed with a very, it's in the lab only. So what we did is just very simple Cartesian robot with 3 degrees of freedom. And this was the sample needle. Actual needle is a little bit different. It was just to show, sorry. So that's the real phantom in which we were trying to insert the needle. Yeah. So what is the problem here? Because we are going to use this system inside MRI, and inside MRI, motors should also be MRI compatible. There should be no magnetism in the motor. So these are ultrasonic motor. There is only one company who is giving a rotary ultrasonic motor in this world, that is Japanese motor, Shinsei motor. And accidentally, currently also I'm using this robot for the groin samples. So currently also I'm working on this MRI compatible robot, not for breast, but for the different region. But my experience with ultrasonic motor was not good. So Shinsei motor, those motors also didn't work properly inside the MRI room. And currently also the motor worked properly, but the duty cycle of motor is very small. So they break down quite frequently. And this also depends on the different type of MRI machines. So there are different type of MRI machines with a different strength. So I use this system with the 0.2 Tesla open coil system, and then there are closed bore systems. And the problem with closed bore system is the you can see in the right side, the closed bore system, the bore diameter is 60 centimeter, and then there is an open bore system. That system has a diameter of 70 centimeter. So when the lady will go inside, this system also should be that compact that it can go inside the bore. And then there is an open system, and in the open coil system, it's the one magnet is on the top and one magnet is on the bottom, and you can easily place. But that system is not that accurate. So with this closed bore system, it can go up to 2 Tesla. The strength of the MRI is 2 Tesla. So these are the things. So these are some, we used a Tesla turbine. So it can be like a pneumatic motor just to use inside the MRI room. And this was the non-electric biopsy gun. The problem here is it's the strength. The initial torque was not that high so that it can move a heavy mechanism. So we were thinking of using a different motor just to give an initial push to the mechanism and then use this motor. Currently, the biopsy gun is also not MRI compatible. So we were thinking about having a pneumatic biopsy gun. So these are the two things on which we were working on. Now the next part is clonoscopy. I worked in a soft clonoscope, and this system is we are going to enter inside the colon just to see that if there is any lesion inside the colon, your intestine. So the problem here is the sigmoid, the sigmoid here, that S part, that the curve part from the rectum when we enter inside, that is very stiff, and we cannot really enter into the main colon because of that the stiff and that acute angle. Currently the system which is working on is it's a Olympus system, and it's very rigid. It can easily go past, and then there is a monopoly of this clonoscope in this industry, and one clonoscope can do at least 10,000 clonoscopies. They just clean it and then do it again, and the problem here is the doctor should have at least 10,000 clonoscopies, 10,000 hours of clonoscopy to do independently, because that's also very painful. Even after sedation, if you can enter, if you twist the colon into different angle, the patient might feel the pain. And I'll show you. Can you see the video? Can you see the video?
Yes, sir. Yes, sir.
Okay. Sorry.
Sir, can you please change your slide in slideshow mode?
Yeah, sure, sure. Now there is another system. It's a capsule that you need to just swallow the system, swallow the capsule. So the capsule system, it's not that reliable, and they did some preclinical trials in China in 2019, because if the orientation of capsule is different, they might miss the polyps. So you might need to insert that capsule different in like 5 or 6. I don't know the number. I'm just giving a random number that you need to insert a different number of capsules, so to make sure that there is a proper screening of the colon. And the second drawback is you might not know that at what location there is polyp, and you need to insert the normal colonoscope to take the sample out, like for the biopsy. We call it the biopsy needle. So still you have to go for the conventional way. So these are the two things. And the second thing is, when we were working on the soft colonoscope. The head was soft and with a different mechanism. The second thing is when we were I'm talking about when we need to design something, and then we have to go for a preclinical and the clinical trials or the dry lab test. In dry lab test, we use pig's colon, because pig's colon is the texture and the stretching, the elasticity of the pig's colon is little bit near to the human's colon. So when we pass the dry lab test, then we go to the preclinical trial, where we use animal, the real live animal, and the dead bodies. We call it cadaver. So in the live animal, it's not that difficult, because the structure, because they, in the live animal, in the pigs, they don't have that sigmoid, that S sort of thing. After rectum, there is no bulge towards the downward, so we don't feel that obstacle. So in pig, we can only test that whether this thing is moving properly, and with the heat of the body, it's the camera is not going off, or all those mechanisms thing. But if we really want to replicate the movement of the colonoscope inside the human body, then we need to test on the dead bodies. And the problem in dead bodies is the freshest dead body. So it sounds a little bit weird. The freshest dead body is 3 months old. So whenever somebody is dead because of all those paperwork or some other ethical issues, we get the body after 3 months. So after 3 months, the colon loses its elasticity and it's very stiff. And for the new systems, they might not work in that elasticity. And that condition is actually not replicating the real working condition. So the real working condition will be much milder, much easier for the colonoscope than working on the dead body. But Olympus is really good in that system also, because it's very stiff. So the soft systems are not good enough to pass the preclinical trials on the dead bodies. So that's the issue currently we are facing in colonoscope. So currently they are thinking about the artificial bodies, which the texture of the colon, because in the colon there are some natural fluids inside the colon which are helping the movement of the colon. There is less friction, but in the dead body the natural fluids are not there, and the friction is more, and the stretchability of the colon is less. Tissues are dying and we cannot stretch it properly, and then there is a perforation. The perforation means then there is a holes in the colon when we stretch too much, or the head of the colonoscope hurts the colon a little bit too much. So that's the problem currently we are facing in the new design of the colonoscopy, the soft colonoscope. So this one was also undergoing a clinical trial in my company where I was working, and this year they were supposed to launch, but because of COVID, it's not the plan was not successful. Maybe next year. Now I'll talk about this, like the final. Almost like final slide, that 3D printing in the surgery. So I just said that the freshest body we get, that is, I'm talking about the adults' bodies, and doctors need to work on the real bodies to practice. and now I'm working in a sick kids. It's the kids hospital, infants or hospital, and if they're and for kids there is no body actually. Nobody donates the kid's body to the hospital to practice. So doctors who are working on heart or cardiology or brain, they don't have a real experience on infants. So basically, what they do, the senior surgeons who are like very experienced in the adult surgery, they just come and help. So here the 3D printing is helping a lot. So this is actually in my lab, Dr. Nabil Hussein's brainchild, and he is a cardiologist. And this, what is going on here? They are practicing on a real heart. The heart which we got is we got an MRI scan, we got measurements, and then we printed it on a 3D printer with a different like textures. The softness is almost like similar, and they are focusing on the real target issues, that in that heart what is the target where they need to do surgery. So they started it in this way just to train the medical professionals, the students which were in the hospital. But after they realized that they might use this in the real surgery. So currently what they were doing, if today they got an MRI scan from the real infant that they need to do surgery in next 1 or 2 days, they give us measurements. We print it like in 1 day. Like if I got a measurement today, I'll give it to my 3D printer manager. He will print it, and within the night they will print like 3 or 4 different hearts of the same size. Next day, the team of surgeons who is going to do surgery, the real time surgery on a real infant, they will practice on the same type of heart in the same situation. So this is the whole is like of the same. The whole of the outside box is this almost like same incision where they do the real surgery. It's just to practice that there should be no surprise in their real surgery. So this is the like heart, and this is the heart on in my hand, like newborn infant, and this is 3 months old, and these all are hearts. In the third picture, these all are hearts, like hundreds of hearts over there for the practice sessions. And this is the brain, and these are all the real dimensions. We printed it in our lab, real dimension, because I'm working in a neurosurgery lab, and my supervisor is a neurosurgeon. So he said that why should all the fun for the cardiologists? So he said that it should be working for we should also work for the neurosurgery also, and we try to print the brain. And there is also like a yearly, semi-yearly brain train, the neurosurgery training on these 3D printed brains. And currently, yeah, this is, we call it the HOST project, and we are trying to help our hospital for doing these kind of stuffs. So I think this is the last. And if you have any questions, any suggestions, if you want anything like what you can do in the Indian setup, you can ask me.
Any questions, please, participants? You can ask questions. It is very interesting and challenging area of research. Dr. Satvinder, R.P. Tiwari here. One question.
Yes,
what material you are using for this 3D printing of the different heart and other things?
We are using this printer. I wrote it down that for this one, and the material was ABS M30i.
So ABS, with ABS, you are getting the same properties like natural organs. Huh?
We are not getting the natural properties. We are getting the natural stiffness.
Stiffness, right?
Yes, yes.
And what wires you are using for endoscopy and colonoscopy? What kind of material you are using for that?
Oh, that was an industrial setup, and that material is not. I was working with the design part only. So and the other part, the outer tube was given to the New England companies. They are like professional for designing the colonoscope out rubber. So that rubber should also be like biocompatible. So I don't know the material of that because I was not in that setup. I was just the in the design part of the bending section. The bending section is the front head where we need to put all the cameras. We need to put all the irrigation channels, how the water will come out, and how the air will go. We call it suction and irrigation. So air will blow out, and there should be a empty channel from where we will insert the biopsy needle, the last part, the scissor, which will take the sample out. So in that part, I was not in the like design of the material. I characterized the robots, the clonoscopes material. I characterized that, but I really don't know that what was the actual material.
Right. Right. Any questions, please, participants? I would request participants to ask questions because it is very challenging and very emerging area of research.
Even if like if
Sir,
there
could
are
you please suggest us what we can do here in India?
in India, there is many things you can do. The only thing is you need to just collaborate. I'll tell you one very simple example. So when I was working in Hong Kong, and my company had a collaboration with Cambridge University, and from there they were working on how to include, because this clonoscope, the end like end part was what they were thinking, that there will be some artificial intelligence in the clonoscope. After like 5 to 6 years, they would launch that artificial intelligence that automatically it will go inside, and they because of the training, they have lots of training with the same set of clonoscope. They can put all those training inside their system, and the clonoscope will move without the help of clonoscopist. So the junior clonoscopist, or you can guess gastroenterologist, can also help doing the colonoscopy, or the senior colonoscope person will be staying a little bit away, and colonoscope will independently move inside the colon, and it can detect because of the machine learning. So this was the end part they were trying to do. It's not applicable yet, and because the problem is the FDA will not give control. Tesla, like just like Tesla car ethical issues, we need to find a way that how we can implement. If we are not designing something like the hard material hardware, we can design it in an algorithm part, design the algorithm part, that how we can make it more safer. This is one thing. Then the collaboration in terms of that in Europe, when I was in University of Napoli, and at least 11 different universities and 23 different labs were working on the same set of problem. So they were sharing ideas. I was little bit like I went there from the Indian setup. With the here we are little bit more like taking all those secrets that we don't want to disclose our project. But there they are more open. They are giving their projects. They are going for the open discussions, and then they collaborate with the different universities. The collaborations are not there in India. So we need to collaborate with the hospital. We need to listen the doctor's problem, then try to make them engineering problem, make that those problems then like translate into the engineering terms, and try to formulate those solutions. We need to start from the basics first, and I think that this colonoscopy will be a very big like project in India, because in the developed countries colonoscopy is very normal. After 50, every person go for colonoscopy. After every 5 years, government is paying all those money. But in India, I didn't even know that this colonoscopy exists when I was in India. So because there is no government help in doing that thing, we can go for the cheaper solution, and that's what we can do. That how we can reduce the cost. If we can reduce the cost, we can even like export these systems to the outside world, and all the African countries, all the underdeveloped countries will be easily targeted using these systems. So this is one thing, and the other thing we need to just discuss with the doctors the real what are their problem. There are many small issues. I'll tell you one more example. When we are removing the like what sorry, we are inserting inside the we were removing the fallopian tube, we are inserting the tools inside the vagina, and there is one person standing over there just to open up. There is a one tool just to open the vagina so that the doctor can easily access the area and they can remove that particular organ. There we just, after like 1 month, we just use one mechanism. We just inserted one same kind of tool. The height adjustment was there, and that doctor's assistant was also removed from that place, because that is really a big operation. They need to change after, because you need to hold it like this way. After 15-20 minutes they will change. So one assistant will change because the arms will go down because of the fatigue of the like human body. So we just inserted one robot. It's not even robot, it's just a mechanism. But we didn't know because we were not there inside the room. The doctors came and they said, okay, we need this kind of stuff. Can you do that? Yes, we can do that. So the basic thing is communication. We need to collaborate.
Right. Thank you, sir. Thank you, Dr. Satvinder, for such an enlightening, informative, and exciting talk. Thank you so much, sir, for your valuable time, and we will be in touch with you. Thank you so much.
Yeah, sure. Thank you.